All right, we are now going to talk about Archimedes' principle. I'm going to start with a little story. The story is of the famous Greek scientist, philosopher, thinker Archimedes, and how the king came to Archimedes with his crown, asking Archimedes to see if his crown was made out of pure gold. But without destroying the crown, how could he do that? Without cutting it, without opening it. And so Archimedes took the crown, was able to borrow it, I guess, and he pondered and he pondered. And apparently he was pondering in the bath with him, the crown. He had the crown in him with a bath. And he was thinking about it, and as he was lowering himself and raising himself in the water, he noticed the water rising and falling. And then he got the insight, and he realized that he could do it. He figured out he could determine whether the crown was made out of pure gold. And he was so excited that he just ran through the streets naked, shouting, "Eureka, Eureka." And that was the story. Well, what we're going to do today is we're going to find out what was that principle that Archimedes discovered, apparently through this interesting story, and how can we use it to determine the density of an object. And briefly, I'm just going to say, and I'm going to write this down in a minute, but Archimedes' principle tells us that when an object is in water, it experiences a buoyancy force. You experience it when you go swimming. A boat experiences it when it's floating. Anything, even things that sink, experience a buoyancy force, which means that there's an additional force acting on them besides the force due to gravity. You still have the force due to gravity, but you have a force that the water is pushing back up on the object, called the buoyancy force. And that buoyancy force is a result of the pressures that we talked about in the last section of the lab. That buoyancy force is going to cause the object to seem like it weighs less when it's in the water. Archimedes determined that the size of that buoyancy force is equal to the amount of the water that the object pushes aside or displaces. So when an object is completely submerged, it displaces an amount or a volume of water equal to the volume of the object itself. So that weight of water that the object pushes aside, which is equal to the volume of that object, is the amount that that object is going to appear to be less heavy. And that's the concept we're going to use in applying Archimedes' principle in this lab today. This is the Archimedes principle written out so you can read it as well as hear me say it again. It says that the buoyancy force that an object experiences when it's immersed in a fluid, it's equal to the weight of the fluid that the object displaces. And what that means is that when the object is in fluid, like it is in this example here, it's pushing water aside. The amount of water it pushes aside or displaces, if you could weigh that water, that's how much lighter the object is going to seem to be when it's in the water. So another way to think about it is when an object's hanging in the air, it experiences basically, let's say it's hanging, so it has a tension force and a weight. When it's in the water, it has a tension force and a weight and a buoyancy force. So there's an additional force in there that's going to make the tension force be smaller. Okay, so that's what Archimedes' principle tells us. What can we do with that? Well, let's take a look. Let's actually write out the forces that are acting on the object in both cases. In this case, it's just two forces. You got tension, you got gravity. The two are going to be equal to each other because that's the only two there are. And the object isn't accelerating, so those two forces have to be equal. Over here, however, you have tension, you have buoyancy, and you have gravity. So the sum of tension and buoyancy has to be equal to the weight, or the force due to gravity. So we can solve for the tension force, and it's going to be equal to the weight minus the buoyancy force. Now let's break down what the weight is equal to. The weight of an object is equal to its mass times gravity. We've known that all along, and I'll call this MO, meaning the mass of the object. The buoyancy force, which is the weight of the displaced water, according to Archimedes' principle, that has to be equal to the mass of the water that's been displaced times gravity. And I can write out the mass as being equal to the density of the object. Density, remember, is kilograms per cubic meter, multiplied by the volume in cubic meters. That product will give me the mass. The mass of the water will also equal the density of the water in kilograms per cubic meter times the volume of the water. All right, so I broke all of that down. What can we do with that now? Now I'm going to pose this question. What if I could find the ratio of the weight of the object to the buoyancy force of the object? I'm going to show you how to do that in a minute, but why do I care? Why is that of interest to me? Well, look at it this way. The weight of the object is equal to the density of the object times the volume of the object, because that product there is the mass of the object. I could just say that. It's the mass of the object. Multiply that times g, and you have the weight of the object, or Fg. Now, if you divide that by the density of the water that the object displaces, times the volume of the water that the object displaces, which is incidentally going to be the same as the volume of the object, for the reasons we just mentioned, times g, then that ratio will be the ratio of the weight of the object to the weight of the water it displaces, or the buoyancy force. I'm going to cancel out objects or items that are the same. So the g's go away, and so do the volumes, because the volumes are the same. So what I'm left with is that Fg over Fb is equal to density of the object divided by the density of water. Wow. Well, what's the density of water? We know it's 1 gram per cubic centimeters if it's pure water, or 1,000 kilograms per cubic meter if it's pure water. So that's its units, either grams per cubic meter or kilograms per cubic centimeter or kilograms per cubic meter. That's what the density of water is equal to. So what this ratio is going to be then, if you just multiply this by the known density of water, you'll be able to get the density of the object. So you could think about it this way. Density of water times Fg divided by Fb is equal to the density of the object. All right, now the density of water, that's known. It's 1 gram per cubic centimeter or 1,000 kilograms per cubic meter. The weight of the object is known. We just simply weigh it. We hang it from a string and measure what the tension is. The buoyancy force is something we can find. We weigh the object in the air, and then we subtract from it its weight in the water. That difference is going to be the buoyancy force. And I'll show you why that's the case. We talked about it earlier, a minute ago, that if you just have the object in the air, it's Fg. If you have the object and it's submerged in water, the tension is going to be Fg minus Fb. So if you take Fg and subtract from it Fg minus Fb, you'll get Fb. That's the buoyancy force of the object. So by subtracting these two values, you're going to get what we're looking for, Fb. So this is a really quick way for us to get the density of an object, and I'm going to show you through a demonstration how we can do that. So what do I do now, you ask? Well, here's the process. What I want to do is I want to weigh the object, divide it by the weight of the object minus the apparent weight of the object, which I'll call Fg prime. And that's the weight of the object when it's in the water. The reason I want to do that is because this is equal to, of course, on top it's Fg, and on the bottom it's the buoyancy force. Fb is equal to the weight of the object minus the apparent weight of the object. That's going to be Fb. All right, so here's how I'll do it. Or one way you could look at how I'll do it. I'll even do it a faster way in a minute. I'll teach you that. But let's say I have some water here. I'll weigh the object as it's hanging here. Here's an object I'll be using in a minute, an unknown object. Weigh it. Weighs whatever it weighs. That's my Fg. Then I'll put it in here. It weighs less now. It's a lot easier to hold it. And I take the difference between those two weights, between the Fg and the Fg prime, which I just determined, and I divide those into Fg. That's going to be equal to this. Multiply that number times the density of water, and that's going to give me the density of my object. And there's even a faster way to do that, but before I do that, I want to tell you that this ratio here, it's not the density. It doesn't have any units associated with it. It's called the specific gravity. You might have heard that before. It's related to the density. To get the density from the specific gravity, what I have to do is I have to multiply the specific gravity by the density of water, and that will give me the density of the object. All right, I'm going to show you a quick way to do this in just a moment. Now I'm going to show you an even better way that you can get the specific gravity of the object from which you can get the density. The first step is simply going to be to weigh the object. So I'll take this orange block and I'm going to dry it off because it was in the water a minute ago. I'm going to mass the object. I get 271.2 grams. All right. Next thing I'm going to do is I'm going to take a small beaker of water, put it on the scale, and I'm going to tare the scale so that it shows me 0. All right, so that's my 0 reference point. And I'm now going to hang the object from a piece of string that's suspended from a fixed position. And I'm going to set it in the water, and I'm going to determine the mass that the scale shows me here. It shows me about 31.9, 32 grams. All right, now the question is, what does that represent? That mass represents the buoyancy force of the water, or if you like, the buoyancy mass. It's the if I multiply it by g, it would give me the buoyancy force of the water. But it is basically the amount of water that the block displaces. That volume is equal to that mass. I just love this method that I read about once. It makes this lab procedure so much better. So what I'm going to do is I'm going to take the 271.2 grams and divide it by the 31.9 grams. And that's going to give me the specific gravity of this orange block, which I'll then multiply by the density of water, and that will give me the density of this block. I'm going to do this for each of the blocks. So I'm now doing it for the blue block. That's giving me a mass of 87.8 grams. All right, so I got 87.8 grams for the blue block. Again, I'm going to put the bucket on here, or the beaker on here. I'm going to tare it. Gives me my 0. And then I'm going to get the mass of this blue block. Whoop. Or at least of when it's submerged. What does it now show me for the buoyancy force? I get about something close to, make sure it's not touching the sides, about 32.1 grams. All right, so you can now find the specific gravity of the blue block, from which you can determine its density, and therefore try to figure out what metal it's made out of. Finally, I have one more block. It is the black block. It's the heaviest of them all. Should be interesting. So I'm going to pop the black block on here. I'm going to untear my scale first. All right, I'll pop the black block on there. 247.3 grams. I'm trying to remember what this one was. Yeah, actually this one was the heaviest. The black one's somewhere in the middle. Alright, so I'm now going to put this on here. Tear it. And what do you think the buoyancy force or the buoyancy weight of the water for the black block is going to be? If you're thinking it's around 33 grams, you're probably right. Let's see. I haven't done it yet, so pretty close. 33 point, varying a little bit. Getting about 33.4 grams. There's a little bit of variation here, variability with my scale in terms of how it's recording it. But I'm going to go with the number I had a minute ago, 33.4 grams is what I had. All right, very close to the other ones. What I just did was I poured the water out of this and replaced it with salt water. And I added a certain amount of salt to the water, and you're going to try to figure out how much I added. But in order to figure out how much salt I added, I have to figure out its density. Now, how do I find the density of a different type of water? The way to do it, actually, is to hang an object that I already know what its displacement was when the water was fresh. Now let me look at what the buoyancy force is now that the water is salty. So I'm going to put the beaker of salt water on here. I'm going to hit tear. There we go. And then I'm going to go with my orange block here. So I'm going to hang my orange block, and if you recall, I think my orange block had a value in fresh water of the buoyancy force, or the buoyancy mass, of 32.8 grams. Let's see what it is now that I have salt water here. Do you think it'll be more, or do you think it'll be less? If I had clickers, I'd ask you to tell me in the clicker, but since we don't have clickers, I'm going to do it like this. I'm going to see what it is, and I think it should be more because salt water is heavier than fresh water. Indeed, it is more. It's almost 10 grams more. 42.3 grams. Actually, it's more than, almost exactly 10 grams more. Actually, let's say, let's settle. I'll go with 42.5 grams. All right, 42.5 grams. That is the buoyancy force with the salt water. Compare it to the buoyancy force with the fresh water. Take that ratio, and that would give you the specific gravity of this salt water. Isn't that interesting how we can find that? All right, that is the last part of this lab. Good luck, and good luck writing it up, and I'll see you in class.